So let's get on to some of the actual course content for today. So there's a couple of things we want to do this week that are a little bit of advanced, not advanced, but a whole new way of looking at things. So that's object-oriented programming. But before we do that, there's a real sort of technical issue that we need to examine, and that's called the issue of equality versus identity, or equals versus is, and it's something that comes up in almost every programming language. So has anybody ever heard of this issue before? Yeah. Okay. So let's examine this issue. So there I've created an array that contains the elements 0, 1, 2, 3, and 4. So there I've created an array, and again, in a different way, created an array that contains the elements 0, 1, 2, 3, and 4. So if I ask, is A equal to B? What do you think that answer is to that? So who thinks it's true? Okay. And who thinks it's false? So it's true. So seems to make sense, right? A and B are both arrays. They both contain the elements 0, 1, 2, 3, and 4 in that order. So that sounds like it makes sense for them to be equal. So A and B are equal. What if I ask A is B? This is something we haven't seen, but this is asking if A and B are the same thing. So this is the identity version. So up here, this is testing equality of A and B, and this is testing identity of A and B. Are they identical? Are they the same thing? So the answer is false. So again, there's A and there's B. So this is saying that A and B are actually two different things. How could I test that? Or how could I prove that A and B are two different things? Yeah. Yeah. So let's change A. So we'll change an element in A. Now A is different, but B is the same. B is what it was before. So this is basically a proof that A and B are two different things. So really, the way that this looks, we should make a picture of this. Is we have this variable called A, and we have this variable called B. The first thing we do is we say A is equal to 0, 1, 2, 3, 4. And that creates this array somewhere, or this list, that contains 0, 1, 2, 3, and 4. And A, so we'll always draw variables as little boxes like this. And really what's assigned to A then is a reference, if you want to call it, or a pointer to this list over here that contains 0, 1, 2, 3, and 4. Next thing we do is we say B is equal to range 5. Well, range 5 creates a list that contains the elements 0, 1, 2, 3, and 4. And then we assign that to B, which really assigns to this little box called B a reference to that list. So when we change A, that goes into A at position 1 and changes it. Notice that B doesn't change. Okay? that clear? Okay, so there's A and B still. What if I say B equals A? Now I have A, now I have B. So if we ask if they're equal, what's the answer? True. And what if I ask if they're identical? So who thinks true? Okay. And who thinks false? Okay. So it's true. They are identical. So when we say B equals A here, what does that do in this little box picture? So the way to keep all of this straight in your head is always to think of variables as little boxes, really little. So you can't put a lot in these boxes. You can't stuff a whole array inside one of these boxes. You can't stuff a big long string inside one of these boxes. In fact, you can't even stuff an integer in one of these boxes unless if it's too long. So when we say B is equal to A, all that says is take whatever is in this box for A and put it in box for B. Well, what's in the box for A? What's in the box for A is a reference to this array here. So we take this value here, we copy it into B. So now B is also a reference to the same array as before, as A. And indeed, we can test that. There's A, there's B. If I say A at 2 is equal to wow, there's A, and now there's B. B was also changed by assigning A at 2. So,
also work the other way around. If you change the value in B, then also change A.
yep. There's B, there's A, right? Because what you're changing is the value stored in this array here. And both A and B refer to that array. Okay? So this is, in programming languages, this is called aliasing. So A and B are two aliases for this array. So you might think of, there's A, also known as B. Okay. So is that clear so far? So can you see this being the source of problems? Lots of problems, right? This is a really common source of errors where you think that A and B are somehow different things, and then you change A, but now B's changed, and that causes all kinds of grief. So let's explore this notion a little bit more. So let's say x is equal to 2 and y is equal to 1 plus 1. So there's x, there's y. Is x equal to y? Yes, they're both equal to 2. X, is it y? Yes? Who says yes? And who says no? Okay. Yes. So x is y. So can anybody explain to me why that is? So let's make a box picture. X, y, each one is a box. These boxes are really small. They can't hold a lot, but they are big enough to hold an integer as long as it's not too big. In fact, they're big enough to hold the integer 2. So when we say x equals 2, what we're doing is just putting a 2 in that box. It's not that x refers to some other thing that's equal to 2. It's just x, the box for x holds 2. And when we say y equals 1 plus 1, we're putting, well, we evaluate 1 plus 1, we get 2, and we store that in the box for y. So we say x equals y. That's true. And when we say x is y, well, this is operator, it sounds like some really deep thing that knows the difference between when things are aliases and so on, but it's actually a really dumb thing. All it does is check to see if what's in each of these boxes is the same. So in this case, this box has a 2. In this case, this box has a 2. Yep.
Is there a formal name for those boxes?
Variables. Yeah, I don't know that there's a formal name for them. It's just, think of it as a variable. A variable is a box that can hold this small amount of information. And if there's too much information, like if you're trying to hold a whole list, then what you hold instead is just a reference to that list, and that list goes away somewhere else. Yep.
When you're talking about the contents of the boxes, the function is, so basically it looks at the origins of the contents of the box. For example, in box Y, the origin of the content was basically 1 plus 1.
Yep.
Whereas in X it was just 2, like it was given to the box as 2.
So the origin doesn't matter. It's just what's in the box right now. So it doesn't matter that that y is 1 plus 1 and x equals 2. That's forgotten. As soon as 1 plus 1 is evaluated, that evaluates to 2, and it's forgotten. It's really just what's inside this box. So if we go back to this picture, we can really understand this. Let's go back, rewind this a little bit. And go back to the original picture where these two things, A and B, referred to different arrays. So when we said A is B, what we're asking is what's in the box for A, is that the same as what's in the box for B? Well, in this case, A contained a reference to this array. B contained a reference to a different array. So these things here were not the same. So A is B is false in this case because what's in these two boxes is different. Later, when we assigned B equal to A, we got to this picture, in which case, yes, what's in these two boxes is exactly the same. It's the same reference to this array over here in memory. Yep.
So what you did before, because they weren't adding up, is because you had the root for A, right?
What's that?
Why they weren't
Identical?
Yeah, why they weren't identical because you had the root for the second value, right?
No. They weren't identical even when they had exactly the same stuff in them. So A and B have exactly the same stuff in them, but they're still not identical. That's because there's one array that contains 0, 1, 2, 3, 4 that lives somewhere in memory. There's a different array that contains 0, 1, 2, 3, 4 that lives somewhere else in memory. A refers to the first one, B refers to the second one. So they're two different things. But the is operator is not that clever. All it does is, so back to this picture, or draw it over just to be completely fresh. Right now we're at this picture that we have 0, 1, 2, 3, 4 somewhere in the memory. We have another one somewhere in memory. A refers to this one, B refers to that one. And in particular, if I look at what's inside these boxes, it's not exactly the same thing. And so is says what's in the boxes is different, so the answer is false. Okay. So actually, it sounds, initially it feels like is the complicated thing that can tell when two things are identical or not. Actually, what's much more complicated is testing if A and B are equal. So when I say A equals B, a lot of complicated stuff happens. So what happens is, first they check that both A and B refer to arrays, and then it checks that those two arrays have the same length, and then it walks through the elements of those arrays one at a time, checking to see that each entry in those arrays is equal. So testing if two arrays are equal, that's actually a fairly complicated operation, but testing if they're identical is trivial. You just look at the boxes and see if they refer to the same thing. Okay. And if you're thinking about performance later, this is sort of an expensive operation, but this is a cheap operation. This is always cheap to check if A is B. Okay. So now we've sort of seen this weird thing that, things look different depending on whether my variables have arrays or whether they have integers, because when they contain integers, then if they're the same, they're identical. And that's because integers are small enough just to fit inside these boxes here. So, so one thing that you'll have to learn then is what kinds of things are small enough to fit inside these boxes. So, for example, are strings small enough to fit inside these boxes? Let's find out. That's the one. So is S equal to T? Yes. Do you think S is T? No. And, well, that's we sort of could have guessed that, right? S and T are these tiny little boxes, and each one refers to a string which is actually fairly long and could be arbitrarily long. Could be, 15 gigabytes of data inside that string. So the picture for strings is this picture, S, T, and the strings live somewhere else. So that's why they're not identical. On the other hand, if I say S equals T, then, yep, they're identical. Because that changed the picture to this one. Okay. So actually, this also tells us something about two things. It tells us about this is thing that tests whether two things are identical. It also tells us about assignment. So when I say S equals T, that's just an operation that takes the contents of the box T and puts that into box S. Yep. You have a question?
Yeah, like how long does string fit in a box?
So there's a special case. So S and T are strings of length 1. Do you think S is T? Turns out that they are. And that's because strings of length 1, do you think this is true? Strings of length 2, strings of length 3, still true. String of length 4. So how long do you think it goes for? We're almost at the point where we should just write a loop now. Still true. So, all right, let's just write a loop. For I in range 20, S equals See if that works. Well, that's interesting. So for 0, it was false. So when S and T were two empty strings, it was false. When S and T were a string of length 1, it was true. And suddenly when S and T are strings of length 2, 3, 4, 5, 6, it's all false again. So that's kind of interesting. So that suggests that there's something weird happening in this case where we're making these strings. And for example, would be different if we did something like this. Do you think S is T? Still true. What if I do still true? So strings somehow, sometimes they're identical, sometimes they're not. It's not clear why. So we should treat those with care, but in fact we'll see in a second that it doesn't matter for strings whether they're identical or not. How about, so what else do we know about? We tested for integers. That seems to be that they're identical if they're equal. Arrays, they're not necessarily identical even if they're equal. Strings, they seem to be a strange case. What else? What other kind of data do we know about? Yep. Booleans. So A equals true, B equals, I don't know, let's say 2. So A and B are both true. A is equal to B. You think that they're identical? Yeah. So Boolean value is about the simplest thing you can have. It's either 0 or 1, and it fits easily into one of these boxes. So for Boolean values, you just have the box either contains true or it contains false. It doesn't need to have any other extraneous stuff in it. So they're identical if they're equal. Other types of values? Any other types of numbers we know about? Yep. Floats. So let's say x is equal to 2.0, y is equal to 2.0. Is x equal to y? That's true. X is, y is false. So floats, they're so big that, that they have to use this picture that looks like this. When you create a float, it goes and lives off in memory. When you assign it to x, x just refers to that float. And any others? So what if I say x is equal to 2 to the power 200? So do you think, so x is equal to y? Do you think that they're identical? No. So false. And so you noticed when we covered the fact that Python can have these arbitrarily large integers, when we inspect them, they always show up with this little L at the end to say that this is a large integer, not just your regular kind of integer. And, you know, people ask, why is it telling us this? Who cares? Well, it's telling us this because it's important. Because now x and y really now are these things that live off in memory. They're actually a big list of integers that you multiply together, or you add them together in a certain way to get the real value. And, you know, when you create them, they're different. X and y are just references to these things. Okay. So for every programming language, you end up having to know this stuff. if two boxes, if a variable can live inside a box, it's usually called, or if a value can live inside a box, it's usually called a primitive value. And typically things like int, Boolean, those are primitive values. And if they can't live inside a box, well, they're not primitive values. Usually then what they use is references, which are primitive values that that refer to those other things. Okay. Okay. So now you know about equality versus identity. It's good that we cover it now. We'll revisit it again a few times because it's a confusing issue for people, and it also interacts with some of the stuff we're going to look at shortly. But I guess one question for you now is, when does it matter to me whether or not two things are equal versus identical? So does it matter for arrays? You know, is that an important thing? Yep.
Yes, because if you wanted to have an array and then make an array identical to it, you have to make sure not to reference the same.
Yeah. So, you know, if I say A is range 5, and then I say B is equal to A, it's really important for me to understand now that if I do something like change B, that I'm also changing A. That's a really important thing, right? That could easily break code. So this could work in my favor. For example, maybe the point is to take a function that takes an array as an argument and then sets its values, changes its values. So then it's important that you know, those changes really happen. They're not just made to a copy of this array. So that's important. What about, for example, for these long integers? Can you think of an example where it would matter if they're equal or identical? No, me neither. What about for these floats? Nope, me neither. What about for strings? Does the example, I mean, the reason it's important for arrays is that if I change an array, that changes everything else that refers to it. Is that an issue with strings? So, can I do something like this with a string? No. Can I do something like this with a string? No. So strings are designed to be what are called immutable objects. You can't change them. If you want a new string, you make a new string. So if you want to modify your string, you can't. All you can do is make a new one that's different from the current one. So actually, it doesn't matter for strings whether they're equal or identical, because, you know, 100 things can refer to the same string. I'm never allowed to change it, so there's never going to be a problem with that. And that's why it looks like Python does some optimizations where if two strings, if it creates two strings which happen to be the same string, it'll just refer to the existing one, at least when it can figure that out. Okay. All right, so in the last little bit, I want to get us to object-oriented programming. And so 10 minutes of object-oriented programming. The best way is just to jump into it. So objects are these things that are supposed to, well, they're supposed to represent stuff. So the programming language people decided that what are things in the world around us, or What are things? Well, they're objects. So object is a generic term for something. So for example, you can make objects that represent a person. You can make an object that represents a table. You can make an object that represents a student. You can make an object that represents a pen, whatever you want. So let's just do it. So here I'm telling Python I would like to make a new kind of object. It's called a person. And it's some kind of object. And anytime you do this, or almost always when you do this, you want to make a function that initializes the object. So something that a person has is a first name and a last name. So I have this function. It has this weird name, underscore, underscore, init, underscore, underscore. That's the name it has to have. And it takes 3 arguments. This one is the first name. This one is the person's last name, so it should be a string. And then there's this special argument called self. And you see that my editor actually highlights self in a different color because this is a word that has a special meaning in Python. It refers to this object. So I want to do something like save this person's first name and last name. Okay. Okay, so now I can say me is equal to person. First name is Pat, last name is Moran. So there's me. I'm a person object. Okay. This is not very interesting. These persons can't really do anything, but I can look at them a little bit. I can ask, what's me's first name? It's Pat. What's me's last name? Oh, it's Pat. Anybody see the bug? Okay, so that's great. So I can define this thing, and so you can think a little bit. This object is a little bit like an array, right? So it's an array. You know, in an array you can have values at 0, at 1, at 2, at 3, at 4, at 5. This object has values at first name, and it has another value at last name. What else? What could we do with a person? Maybe we would like to be able to print a person. So let's say print me. So that's not a very nice way, not a very nice representation of a person. So let's define. So underscore underscore str underscore underscore is a special name for a method that takes an object and turns it into a string. That method happens to get called when you do this. And that also happens to be when you print something, basically you print the string representation of that thing. So what would the string representation of a person look like that would make sense? First name and last name. So we'll return a string that has the person's first name and the person's last name. So notice we define this thing to take one argument, but this argument is this funny thing called self. So there you go. That converts it to a string. So this argument has this funny name called self, and that always refers to basically the object. And if we look at this a little more closely, maybe it's better if we do another method, maybe something like change last name, self, and new last name. So how would we change a person's last name based on what you've seen so far? Yeah. Self.last name equals new last name. Something like that, right? So, me, print me, and me dot change last name to moron. So that changes the last name. So, and now notice this calling, this how I called this. I put me, so the name, the object, dot, change last name, the name of the function, and then one argument. And that ends up calling this function here that takes two arguments. So where is this argument self coming from? Yeah. Yeah, but in this line of code, where does the argument self come from? In this line right here. Yeah. So that first argument is actually what's on the left-hand side of the dot. And it's not really much more complicated than that, because I could, for example, say, this is just a shortcut, so let's check this out. So this syntax of saying me dot change last name is really a shortcut for calling this function change last name, first argument me, second argument whatever was provided. Okay. Now this is longer and more long-winded. This is somehow a cleaner way to do it, and it also represents it's a little bit more readable in the sense that it's sort of saying to me, me, change your last name, instead of some weird thing like person.change last name me more. And this is somehow a little bit more readable and also shorter. Okay. So these objects that we create, they have data associated with them. Those end up being called members. So this is first name and last name are a member. And they also have functions associated with them. Those are usually called member functions. In this case, there's init, string, and change last name are the member functions for this new thing we've created. And of course, we can create different people. So there's two different people. Do you think me is you? No, right? Person is this fairly complicated object. It seems unlikely that person could fit inside one of those little boxes. And even if it could, these two persons are different, so me is you is definitely not the case. So think about that for a little bit before next class.